Okay, so now that we have learned the formulation of the capacitated plant location problems, now we are going to solve it. So we are again continuing still with the SunOil example from the Chopra Supply Chain Management book from the chapter 5. So in the previous video, we have learned about the given data and the formulation of the problem, and we have simply put that information here in this first table, as you can see. So normally for this kind of cases, when we have this data given for each of the supply locations to each of the demand locations, normally I will always create a similar table, okay, exactly with the same formations, where I will have my volume after optimization, okay, and then if I have the same format here and here, it becomes easy for me to multiply the values of cost with the volume and then form the objective function. Okay, so that is one of the reasons. So in this case here, this part are going to be our decision variable. So here, this part, they are for the Xij, how much are going to be sent from each of the supply locations to each of the demand locations. So let's say I'm going to color it with something like this color. And here in this part, we are going to get the values of the Yi, the binary variable constraint, where if my plant is open, if my low capacity plant is open, I will get 1 here, or if it's closed, 0, and high capacity will come here. So I'm going to mark these two also with yellow. Okay, so here maybe it could be a good idea to write low plants. Okay, and here it could be good idea to write high plants. So plants mean production plants. Okay, so now here we will get our outcome. The total one, we not necessarily need it, but normally I would like to add the local and high. So sometimes it is useful to give a constraint to force that total has to be 1, so that we will not have 2 plants open in each of the locations. So for example, now if I put 1 here and if I put 1 here, it becomes 2, right? I changed the color here. Yeah, I turned it back. So if I put 1 here and if I put 1 here, then we have 2 plants in North America. Sometimes we want to force the model that no, give us only 1 plant per supply region. Okay, so that's why it is good idea to have this total plant column here. But I'm now going to remove these both ones from here because that's something we should get from the optimization. But I am going to drag this one up to this point. So it's just the sum of the 2 columns here for plants. And in general, I always think it's a good idea to have the optimization equations in one of the corners in the Excel file. Then it becomes easy to follow the equations and implement them here. So here I copied the set of equations. So here we have the constraint. The first constraint is here about supply, and the second one is going to be about demand. Okay, so let's say if I put some color here, then it's easy to see. So this part is going to be supply related constraint, and this part is going to be demand related constraint. So the supply related constraints, that corresponds to the second equation here. Okay. So the supply related constraint, that corresponds to the second equation here, right? This one was our supply related constraint. And this was what about demand. So normally when we have equations like this, it is always a good idea to move the decision variables in one side. Okay, that the variables in one side, and then have a numeric value on the other side. So for example, for this one here, if we convert it to dj minus xij equals to 0. Okay, so this was our demand in the demand location, and this was our all the supplies to the demand location from the 5 supply locations. Okay, so when we deduct the demand in each of the location, so if I just quickly draw it here again. So let's say this is our D1 and this is our S1, and then up to S5, and here we have up to D5. So at each of the demand location, we can get supplies from everywhere, right? So when we deduct from D1 the demand minus all the supplies we got from all the 5 locations, then what we get? We get if our demand is met or not. If our supply and demand are same, then it means all the demand are met. Okay, all the demands are supplied. So then it should be 0, right? If the demand supplied to the location is same as the supply, as the supply to a demand location will be same as the demand value there, then it will be 0, right? So simply, for example, here, let's say if I think about D1 is 12. So all the supply to D1 should be equal to also 12 million units. Okay. And that simply means if our demand is met or not. If the value of this part is not equal to 0, if the value of this part is not equal to 0, then what does that mean? So let's say the value is a negative value. Let's say -2. What does this mean? The supply is more than our demand. Is that a problem? Okay. So to get a negative value, let's say for D1, what has to be true? So for example, here we know, if I just move it a little bit down here. So the demand at D1 is 12. And if our supply to demand location is 14, only then we will get a value of -2. Okay. That means we have supplied more. Is that a problem? In general, no problem. We have supplied more than our demand, but then it will cost us money. So we don't want to cost unnecessary money. Okay, so that's why we want it to be 0. When will we have a positive value? So if 12 minus, so 12 was our demand, and then if we supply to that location from all the 5 locations, if we supply 10 units, then we will have a +2. That means our demand has not met. So we are losing sales. Our demand was 12 million. We sent 10 million. So we're losing sales, right? So that is why we force it to be 0. That's our demand, unmet demand equation. So let's say, as we already discussed this, let's put it first. Okay, we will put the supply equation later. So here are our cells for this unmet demand. Okay, here, actually this part here. So to get the unmet demand for each of the location for North America, I will start with the function equal to, I will select the demand for North America minus sum of all that we will supply to North America. Okay. So this is where after the optimization, we will get the values that the volume that will be transported to North America from all the 5 locations, right? So we just take the sum of it and we deduct it. And then we can just quickly drag it. And just to double check, we double click and see that, yeah, for Africa, the equation is like the demand for Africa minus all the supplies to Africa. Okay. So this is what we call unmet demand. And it has to be 0. Okay. So all demand has to be met. So it has to be 0 after optimization. Okay. Now let's come to the second equation here. So here, the idea was that in the second equation, in the supply equation, the idea was that we have these 5 supply locations, right? Supply locations, and we have these 5 demand locations. Okay. And here, the idea was that each supply location can serve to all the 5 demand locations, right? But the capacity of each of the location, it cannot be exceeded when serving the demand. Okay. So all the demand that will be supplied from each of the location has to be lower than its capacity. So that's what we said. Sum of all xij for each of the supply locations has to be less than equal to kij. So if we again want to move all the decision variables in one side, then we can convert it like this. So we can say ki and then yi minus xij. So we simply move this one to this side. That's why you use the term minus. But when we move a variable from the left to the right, and then we have a less than equal to sign, it is going to flip. So that's it's mainly based on the basic arithmetic principles. Okay, it will flip the side. Just for information, if we're moving from this side to this side, so if we were writing xij minus kiyi, then we would not actually flip the symbol. And the thing is, both are same. This one or this one, both are actually same. It will give you the same result. But we are going to follow this one. Okay, just easy to follow. Okay, actually both are easy to follow. So, but we are going to follow this one. Okay, so here we first have to define the capacity minus all that is supplied from that capacity location. Okay, so let's come here. Let's start with North America. So here we start with the function. So what is the capacity that we have in North America? The capacity we have in North America is here, first the low capacity multiplied with if that low capacity plant is going to be open or not, plus the high capacity multiplied with if that high capacity plant is going to be open or not. Okay, this is our total capacity in North America. And then we are going to minus all the delivery from North America. So sum of all the deliveries we are going to make from North America to all the demand locations. Okay, that's it. So we simply put this part of the equation. Okay, the left hand side of the equation, we put that here. Then we are going to drag it. So here all the values are 0. That's because we don't have any solution here yet. So that's why these values are 0. Okay, and that's okay. And we have one last thing to format here. That is our objective function. Okay, this one. If yi multiplied with fi multiplied with yi plus cij. So first part is the fixed cost for the plants, and then second part is the variable cost for how much we deliver from each of the locations. So we are going to define it in this cell here. Okay, the cell is B31. So in this cell here we can see the cell number, right? So in this cell we are going to define this. So we start with the function equal to. So first we are going to put all the fixed cost. So we are going to use a function called sum product. Okay, sum product fixed cost of my low capacity plant. Okay, and here I see I have to use a semicolon. After array you see I have semicolon, so I'm going to use semicolon. In some computers you might have to use a comma depending on which format of Excel you are using, if you're using the American one or the European one. So here I'm going to put a semicolon, and then I'm going to select this part here. So the fixed cost should be only accounted when the plant is open. Okay, and here we will get 0 or 1, right? So that's why we multiplied with this one for the low capacity. Okay, plus you can see here on the top my equation is continuing, plus again sum product, again sum product. Here I'm going to select the fixed cost for the high capacity multiplied with the fixed cost if the high capacity plant is open or not. Okay, so we are going to multiply with that, and then my bracket close. Okay, So this part is only the first part, that fi multiplied with yi, so only this part. But then we have to add this cij multiplied with xij. So that's all the cost multiplied with their corresponding volume. So again, we are going to write some product. You can see the equation is continuing here on the top. Okay, some product. Then I'm going to select all this cost function, all these cost cells. Okay, semicolon. These are not cost. This is where I will get the volumes. Okay, so these are my all these cost cells. Okay, multiplied comma semicolon. Yeah, semicolon or comma depending on your computer. Semicolon, and then the volumes that we will get here. So all the cost values are going to be multiplied with their corresponding volumes that we will get after solution. So this is how we put the objective function in this case. Okay, and we are going to press enter. So here our objective function equation is set. You can see it on the top here. And when you click here, actually it's highlighted all the cells that it is using. So you can quickly have a look. Okay. So now this part is done. Now we are going to put the constraints in the solver and run the optimization. But first I'm going to clean this write-ups here. So I'm going to simply close this. Now we go to data. When we go to data, we can see my solver is here. So I'm going to click here to run the solver. So in the solver here, we are going to first select the objective function. So I click here and then I click this cell. So that's my objective function B31. And we are going to minimize it because it's a cost problem. So cost problems are normally minimization problem. Profit problems are normally going to be maximization problems. So we are going to minimize this cost problem. And here by changing cells, here we can actually select all of them up to this point, not the total one. Okay, but the values that will be determined by the optimization. The values corresponds to this part here, like how much will be delivered from one location to another location, and if our plants are going to be open or not. So in the formulation problem we discussed, we mainly have these two variables, yi and xij. These are our main two decision variables. Okay, so we select them here by changing cells. Now we have to add the constraints. So we had mainly these constraints here: supply constraint, demand constraint, and then binary constraint and non-negativity constraint. So if you remember, we did the formation. If I just actually bring the equations again. So we are first going to define the demand constraint, dj minus xij is equal to 0, which we have set in the unmet demand. So I'm going to click here, add. And here in the cell reference, I'm going to select this unmet demand cells. Okay. And I'm going to say they should be equal to 0. Okay. So I'm putting this one, the j minus xij, which we already defined here in unmet demand, it should be equal to 0. Then I'm going to click on add. Then the second one, ki yi minus xij, which we defined here in excess capacity, should be greater than equal to 0. So I'm going to select this part here, and I'm going to say it should be greater than equal to 0. Okay. Then I'm going to add this. Then my binary constraints. So here the low capacity plants and high capacity plants. So I'm going to select these two rows here for these low plants and high plants. And I'm going to say they are binary, and I'm going to add them. Then non-negative constraint, xij should be greater than equal to 0. So here we will get all the values of xij. So here the idea is that the volume that we are going to transport, they should be 0 or higher. They cannot be negative. We cannot transport negative values, negative volumes. So it should be greater than equal to 0 once again. And then okay. And this is simply how it looks like, our formation of the optimization problem. And then we are going to solve it. So here we have 3 optimization algorithms. simplex, GHG linear, and evolutionary. So it might solve with the simplex. So let's give a try if we can solve it with the simplex. If not, I will try the nonlinear one. And it actually solved already with the simplex one. And we see this is our solution, 23751. Okay, so I'm just going to color it and highlight it. So this is how actually we can solve a capacitated plant problem. Okay, so where we have constraints and we are going to find out the network structure of the supply chain design. Great, thank you.